Welcome, everyone. Good morning, good afternoon, good evening, wherever you are in the world today. Thank you so much for being here. My name is Sarah Alspawn. I will be your webinar host coming to you live from Cincinnati, Ohio, here in the US. I'd like to welcome you to today's webinar, our topic, Accelerate Electrical Schematic Creation. And I would like to welcome and introduce our speaker today. With us, we have Kevin Moran. I will briefly read from his bio here and then turn things over. Kevin joined the Siemens Mainstream Engineering Global Technical Enablement Team in 2018 with the primary objective of focusing on the new solid edge electrical design products. In addition to providing product expertise to customers, Kevin assists with the creation and distribution of marketing, sales, and pre-sales collateral. He has been involved in design engineering and manufacturing for the past 25 years. A large amount of Kevin's time has been spent working in the CAD/PLM industry. This has been a combination of working for channel partners and at the vendor level. Kevin has also worked within the additive manufacturing industry for a number of years.
Welcome to today's global webinar on accelerating electrical schematic creation with solid edge wiring design. My name is Kevin Moran. At Siemens, I am a senior applications engineer working in the global technical enablement team where I'm responsible for our electrical design solutions. We'll start today's session with a quick introduction to the solid edge portfolio, and then we'll take a deeper dive into the applications that are available in the solid edge electrical design segment. The main focus of this webinar will be to look at solid edge wiring design in action, to show how the intuitive, powerful, and intelligent capabilities help to accelerate electrical schematic creation. A further demonstration will dive into the downstream benefits that can be leveraged from the reuse of the schematic designs. And finally, we'll round out the webinar with a summary and a Q&A. Solid Edge is a key part of the Siemens Accelerator portfolio and is focused on the requirements of small and medium-sized manufacturers. Solid Edge enables manufacturers to create a comprehensive digital twin of their products and includes solutions for mechanical design, electrical design, simulation, manufacturing, and technical publications. It also includes solutions for data management for the technical data that is created and consumed when supporting the comprehensive digital twin. It facilitates collaboration both within manufacturing companies and with external resources including suppliers and customers. Solid Edge is on the ramp to digital transformation. If we take a look at the core capabilities and packaging of the Solid Edge portfolio, we'll see a cross-product capability is provided that enables the complete portfolio to work together. For example, ECAD working with MCAD, validating the digital twin with simulation tools and more, using the digital twin to create technical documentation, and so on. The Solid Edge portfolio offers so much more than just cross-product capabilities. From Teamcenter integration to annual releases, cloud-based licensing, either on-premise or in the cloud, to perpetual or subscription offerings. All of this while providing a sound investment and best-in-class data protection. The electrical design portion of the Solid Edge portfolio comprises of 4 capabilities with the addition of a PCB design solution. Electrical routing is an add-on module available within Solid Edge that allows for real-time seamless integration with solid edge wiring and harness design, providing a true and consistent ECAD/MCAD experience. As well as this, wiring and bundle runs can be created in 3D to provide accurate length information that can be shared with the ECAD applications. Solid edge wiring design is an electrically aware schematic tool for designing the wiring of electrical systems for multiple industries. For example, industrial machinery, specialist vehicles, consumer devices, or medical equipment. It comes with built-in verification and design rule checks to ensure that products are optimized for their performance and reliability. Its intelligence parts library helps drive the design process with automatic part selection. Solid Edge Harness Design provides rapid, intuitive harness and formboard design tools with automated part selection, design validation, and manufacturing report generation. PCB Collaborator brings the electronics and mechanical worlds together, providing a seamless passing of PCB information between Solid Edge and many ECAD solutions. Within the wider Siemens portfolio, we also offer PAS Professional, which is an affordable, intelligent, an integrated design and verification tool for PCB engineering projects. In this first demonstration, we will create a simple circuit showing how parts can be found in the library, how the system helps authenticate the circuit as you work. Then an analysis of the circuit is done to ensure cables and components are correctly paired before a single wire is run, and finally output reports and running lists are created for downstream manufacture. For the purpose of this demonstration, we're going to show intelligent wiring using an industrial cleaning machine from one of our Siemens customers, WashTec. This project is made up of a number of circuit diagrams. We'll open the power circuit. Notice how easily we can navigate around the sheets. Just select the link and it opens the target as easy as that. Here on the power circuit, we see that the contactor that operates the pump. This is a composite symbol which we will be using to demonstrate the creation of an intelligent circuit. Let's open a new sheet for the control circuit. If we know the library and the location of the symbols, as we do here, we can navigate to it. Additional copies of the symbol can be placed by simply using copy and paste. The numbering is taken care of to ensure all components are unique within the project. If we don't know where the symbol is, we can use the filters and in this case we enter pull and it navigates to where the pull switch is located in the library. A simple drag and drop onto the drawing sheet and the symbol is placed. The normally open contact and relays are elements of the contact KM4 that we are controlling, and as such we can specifically reference those here. Note how it links to an existing component and does not place a new one. Now we can rename the components if required. If we add the same name as one already in the project, then the DRCs, the design rule checks, come into action, indicating it in red that it is already in use and cannot be used. Once all the naming is done, we start the wiring. A simple add wire and select the connect points on the devices adds the intelligent wires. Finally, we'll add the wires for the switch and chamfer the wires to indicate which contact it's wired to. Now let's add the composite symbol as a reference node. See how the cross references are automatically added to the circuit. If we return to the power circuit, we see we need to wire in another motor. This can be easily done by doing a copy and paste of the existing circuitry consisting of both wires and components as we're doing here. Note on the copy of the component designations are updated based on company numbering standards. These and additional properties can be edited based on requirements we see here. Remember, properties can be hidden or shown by a simple click in Properties or project-wide in the styles. We'll finally finish this off just by adding 3 new wires, and it's a very quick selection in a multi-fashion to have them all added. Next, we'll take a look at the analysis. This can be a simple analysis where we just check for continuity, or a more in-depth numerical analysis where we take into account voltage, current, and resistance of components and wires along with their analysis models to determine how that circuitry will perform. In this example, we are looking at the interlocks on the doors of the WashTec machine. For safety, all of these switches need to be closed before the machine will operate, as indicated by the light tower's red, green and orange conditions. We select the main control switch that sets the interlocks to closed, and we see that the green light turns on. Notice we can also interrogate each device and wire to check that it is not under or oversized, ensuring optimum integrity of the circuit. We can also introduce failure conditions on devices to further check the results. Next, we will simulate pressing the emergency stop switch while the machine is running. This will break the circuit and stops the machine as indicated by the light towers changing to a red and orange. A simple resetting of the switch re-establishes the connection and the machine can continue. Finally, let's look at the output reports. These can be either ones delivered out of the box, such as the bill of material and running list, or they can be configured to your company's specifications using the built-in report builder. Remember, all this is being done on a virtual model before any wires have been run. So, we've just shown a brief overview of how the solid edge wiring tools with the built-in libraries provide design consistency whilst creating intelligent schematic diagrams. We showed how the design rule checks work behind the scenes, giving continuous feedback and leading to better quality right first time schematic design. Reports are generated automatically from the linked schematic diagrams, allowing for late changes to the designs to be incorporated quickly and easily. In this next demonstration, we'll take a look at the downstream benefits of reusing the schematic design data. We'll focus on two main areas: creating a layout for our electrical control panel and the generation of a terminal plan table. We'll show how we can add backboards and industry standard mounts and channels. We'll then populate the components on the rails by reusing the information from the schematic diagram. And finally, we'll create the terminal plan that can be shared with manufacturing. Taking a look at another Siemens customer example from Finamac, here in the wiring design, we have completed a multi-page schematic which belongs to Finamac's pop circle machine. The pop circle machine contains two electrical control cabinets. To assist in the building of the control panels, some additional documentation is required. Solid edge wiring design includes a layout design capability that allows users to reuse the schematic intelligence to generate a panel layout. We'll start off by placing a drawing border which contains the correct size cabinet that we need. The layout design toolbars provide us with new capabilities to place mounts, channels, and other hardware. We need a mounting plate, so we'll select the other command and draw this to size. We'll assign a name and designate the type as backplate. The lengths and widths can be fine-tuned as required. We need some wiring ducts, so we'll place a horizontal channel. Dynamic dimensions provide accurate feedback. We can quickly access the properties, and the channel type can be modified by selecting from industry standard profiles that are available. We need two further channels. We'll place a vertical member first, and then we'll do a copy of the horizontal member. Two DIN rails are needed for the electrical components to attach to. Using the mount command, we'll position the first rail, and then we'll place a shorter version in the lower half. Just like the channels, the properties can be accessed. The profile types can be changed, selected from different industry standards again, if needed. To help with building the panel, we'll add some dimensions to the mounting plate, given the height and width, and then we'll add some vertical dimension to the channels and rails to document their positions. In order to place the electrical components onto the rails, we need to associate the layout design to the schematics. This is easily done by selecting the Associate Design icon and choosing our design. On acceptance, the logical objects on the schematic are synchronized to the layout design. Inspecting the design browser, we can see we have some new unplaced devices. The mounts, rails and backplates are also visible. The Groups tab is useful to categorize specific information. In the case of the layout design, we have two folders splitting the devices into Zone 1 and Zone 2. Placing devices is simple, and there are many ways in which this can be achieved. We'll start off by placing a single device, snapping to the center of the rail. Options to rotate are available if needed. Multiple devices can be placed at the same time. The spacing between the devices is easily achieved with a press of either the 1 or 2 keys on the keyboard. The order in which devices are selected in the browser dictate how they are positioned on screen. Here we'll select K6 first, then the subsequent devices. Pressing the O key reverses the order of the devices. The P key switches to manual mode, so individual devices can be placed, splitting them from the selected group. We'll place another run, again selecting in the order we require them to be placed on the rail. We'll finally place the last few devices on the top rail. The Zone 2 folder contains all the terminal devices which belong to the bottom rail. We want these to be in 3 distinct terminal strips, so we'll place them as 3 groups. A few dimensions are required to detail the position of the terminal strips on the rail. Moving the middle terminal strips shows the dimensions dynamically updating to reflect the new position. A quick zoom shows that the component names have been populated underneath each of the devices for clarity. A bill of material has automatically been built as we've added the devices to the layout design. The bill of material is customizable to show the information required. BOM IDs can be easily generated, resulting in balloons being added to each of the devices on the panel. The final deliverable required is a terminal plan to assist in the assembly and wiring of the terminal strips. This is easily achieved by creating a new diagram in the Project Design folder. The terminal plan tables are automatically generated, documenting the terminal blocks along with their specific symbol, physical sequencing the strip, and details of where the wires terminate at both ends of each block. Single and multi-level terminal blocks can be modelled as required. As the table content, including the connectivity, is reused from the schematic design, any changes made downstream will automatically be reflected, providing accurate and up-to-date information. Moving to the Groups menu, we can add a customized filter criteria to show the separate terminal strips in the browser. So, we saw how the components populated from the schematic diagram were easily placed on the rails using a simple snapping and auto positioning. We made sure all the equipment fitted correctly, and finally we created terminal plans to ensure the panels are manufactured right first time. So in summary, we have just shown a brief overview of how the solid edge wiring design tools with the built-in libraries provide design consistency while creating intelligent schematic diagrams. We showed how the design rule checks work behind the scenes, giving it continuous feedback and leading to better quality, right first time schematic designs. Reports are generated automatically from the linked schematic diagrams, allowing for late changes to the design to be incorporated quickly and easily. We saw the reuse of data, with components populated from the schematic diagram easily placed on the rails using simple snapping and auto positioning. We made sure all the equipment fitted correctly. We created output terminal plans to ensure the panels were manufactured right first time. So, with solid edge wiring design, you can enhance your time to market, enhance your product quality, and greatly improve your profitability. Solid edge wiring design, you get your design right first time.
And this concludes today's webinar. Thank you so much for joining us, everyone, and have a great rest of your day.